Welcome to today's video. In this video, I'm going to talk about the fundamentals of how surveying equipment works. More precisely, how terrestrial surveying equipment works. We're not talking about satellites here or anything like that. We're talking about the run-of-the-mill surveying instrument that you see on the side of a road or on a construction site or out in a field somewhere, set up on a tripod, more often than not with some person standing behind it looking through it and punching buttons. And I'm here to explain basically how it works. And it works very simply. The important thing to remember going forward is that surveying equipment, a modern total station, for example, we're not talking about the old stuff. The old stuff was pretty cool, but we're not talking about that. A modern total station functions by measuring three things and three things only. That's very important you understand. The only thing the modern total station, or an antique total station for what have you, for what that's worth, the only thing it can measure is a horizontal angle. That means it measures the angle horizontally between given points. For example, I'm looking at the camera. If that's 0 degrees and I go over this way 90 degrees, I've just measured a horizontal angle. That's what it does. It measures horizontal angles. Imagine looking down from the top and seeing the surveying instrument turning an angle. The other thing it measures is vertical angles. In other words, if you were looking at the instrument from the side, if the person is looking through the scope perfectly horizontal, then he's horizontal. If he's above horizontal or below, it records those angles. Traditionally, it records them with respect to vertical, the zenith. Technically, it's called a zenith angle. I'll talk more about that here in a minute. So it's measuring angles turned horizontally, angles measured vertically, just like this, and then, thanks to the laser built into the thing, it measures a distance to a point. Generally, it measures to a reflective prism, but a lot of total stations are reflectorless. They can measure a distance to any reflective surface. It comes in handy a lot of times. But that is basically all they do. Now, if you look at the instrument itself and the digital readout on it, very often it will give you a horizontal distance and a vertical distance on that instrument display. And that's very useful information. But in the raw data, in other words, the information that goes into the data file straight out of the instrument itself, it really only has the horizontal angle, the vertical angle, and the slope distance. All that other stuff is mathematically derived from those 3 points of raw data. And I'm going to explain a little bit about how that works right now. Now, the first thing to remember is that when it comes to surveying, the distance measured along a slope is largely irrelevant. Irrelevant to topography, irrelevant to boundary mapping, irrelevant to highway design, what have you. Anything in that regard. The slope distance, as it is called, is largely irrelevant. In the field, we are concerned with horizontal distances and vertical distances. What that means is, when you have an instrument that is not oriented perfectly horizontally, and you measure a distance, that distance is going to have a horizontal component and a vertical component. And to illustrate that, I'm going to draw a little sketch up here on the whiteboard behind me. Now what we're going to be looking at in this sketch is we're just going to be looking at, imagine looking at a surveying instrument from the side, off in the distance, and you're going to see what it does. Here we go. It's a field, it's green grass. You have your surveying instrument set up right here, and there's the field. Down here on the bottom of the hill, you have a tripod set up with a surveying instrument on top of it. Right? 3 legs, survey instrument looks like this, got a scope on it. Not the greatest artwork in the world, but you get the picture. Literally and figuratively. Up here at the top of the hill, we have a pole with a prism on top of it, right? There's our prism. It's on top of that pole. Instrument, prism. Well, the instrument operator, or the robot, as the case may be, points the instrument at the prism. I'm going to draw the rays of light going from the laser to the prism. You get the concept. All right, it has just measured this distance, slope distance. It just measured that slope distance. But, like I said a few minutes ago, that slope distance is not really usable. It has to be reduced to a vertical and horizontal component. And that's where the angles come into play. If 0 degrees is up here, because that's the way the instrument works, and you have an angle here, zenith angle, I'm going to call it the zenith angle. Well, if you know that angle, and you know the slope distance, and you want a horizontal and a vertical component, well, that becomes fairly straightforward to do. Lo and behold, you got yourself a right triangle. So, with that angle and that slope distance, you can then figure this distance and this distance, and the math is relatively simple. Got a right triangle, you got the SOHCAHTOA acronym and all that other stuff. Remember, the sine of any angle is equal to the opposite side over the hypotenuse. In our right triangle here, the slope distance is the hypotenuse. So the sine of the zenith angle that little symbol right there represents angle. Sine of zenith angle is going to be the opposite, the sine is the opposite over the hypotenuse. So it's going to be the opposite, which is the horizontal distance, over the slope distance. Sine z, the zenith angle, is going to be HD over SD. Well, you know the slope distance, you know the zenith angle. You just got to rearrange to get yourself a formula. And that formula is this. HD is going to equal SD times the sine of the zenith angle. There you go. For your vertical distance, you're trying to solve for the adjacent angle. which means you'd be using the cosine instead of the sine. So our vertical distance is going to equal the slope distance times the cosine of the zenith angle. And that's what the instrument's doing. That's what your data collector is doing. If you have a separate data collector plugged up to your total station, the data collector just gets those raw angles and it does the math to figure the horizontal distance. You can do it manually too. Perfectly legitimate way of doing it. But that is what your surveying instrument is doing. Everything else that it does is mathematically derived from those three measurements: slope distance, zenith angle, horizontal angle. That's the basis of it. Just a minute, we'll do some examples and you can see it applied. And it gets more and more complex as we go forward. But those two formulas serve you in good stead. When you get back to the office after a surveying job and you download your data, you're going to download a bunch of files. Depends on what software package you use. But somewhere, no matter which software package you use, if you're using a total station to do your surveying, somewhere in there, you're going to have those same three pieces of information. You can look in the raw data file. Different software packages call it different things, but it's all basically the same concept, raw data. It's in there. Those two formulas, absolutely critical and absolutely basic. And that's how it works. A few minutes I'll draw an example up here and we can take some imaginary survey data and turn it into something really practical. That was step one. Thank you for your time. Look forward to carrying this forward for our next video. Thank you. Hello again, and welcome to our follow-up video about how surveying instruments work. In the previous video, I explained horizontal angles, zenith angles, and these two formulas that simply give you the tools to reduce slope distance and zenith angle to a horizontal and vertical component. Now, we're going to give a little illustration of that. Nothing works better than an example, so I'm going to draw one up here on the board. We're going to solve it and hope for the best. Here we go. Once again, remind you that all these things are made up on the fly, so if we make a mistake, we're going to have a challenge figuring it out. Here's our side view of our problem. We're going to start out right here. We've got our surveying instrument down here on the tripod. Once again, there's the tri-brac, there's the standards, and there's the scope. Okay? And it's pointed up here at a prism on a pole. You see him standing on the side of the road, probably. Little prism on a pole, usually with a guy holding it, occasionally a girl, trying to keep it vertical. Occasionally you will see a prism set up on a tripod. That is something called a dead man in the business, and that allows you to turn a stable and precise angle to a target. And it allows you to turn a stable and precise angle to a target over and over again. So there are advantages to that. But nonetheless, back to our illustration. We've got our surveying instrument set up there. We pointed at prism. We measure a slope distance of 43.5 feet. Now we'll make it more precise. We'll make it realistic. 43.50 feet. Now, we got a zenith angle in here. Remember, on a zenith angle, 0 degrees straight up. We got a zenith angle of, let's say 74 degrees 18 minutes. All right. Remember, in this business, everything's measured in degrees, minutes, and seconds. So that's our raw data. We're not worried about the horizontal angle right now. We just want to reduce this to a horizontal and vertical component. So once again, remember we have our right triangle in here. This is horizontal distance. This is vertical distance. Same thing works out with our formulas up there. So we're going to take these formulas, we're going to apply it to the situation at hand. That means we have a horizontal distance. Using that formula right there is a slope distance of 43.5 times the sine of 74 degrees 18 minutes. Do some quick math with the calculator. We have a horizontal distance of 41.88 feet. .88 feet. And that's rounded to the nearest hundredth of a foot because that's how we do it. Theoretically, it's 41 point some long number, but 41.88 is good enough. Our vertical distance, that's our horizontal, our vertical distance is going to equal 43.5. 0 times the cosine of 74 degrees 18 minutes. 4350 times the cosine of 74 degrees 18 minutes is 11.77 feet. Correction. 11.77 feet. I was right the first time. 11.77 feet. So that means this distance from here to here, 11.77. And horizontally, we have 41.88. And it goes from the prism pole to the instrument. And there, you just reduced a slope distance and a zenith angle to its horizontal and vertical components. But now, I'm going to throw you a little bit of a curve. Your instrument is measuring from the center of the instrument itself to the center of that prism. Problem is that other than in an academic sense, we don't really care about the instrument or the prism. What we care about is the points on the ground. We're out here surveying the surface of the earth, right? So, that gives us a bit of a problem because the horizontal component is fine. Assuming the instrument is set up vertically over the point, and assuming the prism pole is in proper adjustment and held vertically, the horizontal distance between this point right here under the instrument and this point right here under the prism pole, we know that this horizontal distance is 41.88. There you go. We know that's 41.88. But vertically, we got something else going on. This instrument's set up on a tripod. It's 4 or 5 feet above ground. This prism pole is, if it's not extended way up, is probably about 5 feet tall. So we have to account for that. And it kind of makes common sense, but we're going to go over it anyway. So the concept here is this point you've occupied occupied point. In this business, we call that the occupied point. Wherever the instrument is sitting, where the instrument is set up over, is the occupied point. The occupied point has some real elevation, whatever that may be. That's what we care about. We care about this point right here. The point we just shot. It could be a foresight point, it could be a backsight point. Doesn't matter. That's what we care about. How do we find out the elevation of that point? That's where the height of the instrument and the height of the prism pole, or the height of the prism, height of the target, I guess would be the better choice of words. This distance here from the ground to the center line of the instrument, we're going to call it HI, for the height of instrument. Now in leveling you have HI as well, but that's a whole different instrument, different procedure, different concept. Don't get the two confused. Right now we're talking about total station. HI. The HI in the context of this process is the height of the instrument above the point. And as a matter of fact, on the side of every instrument, you see a little dot, and that dot measures the center of the instrument that you're supposed to measure to when you set it up. Up here, we have a prism pole. Now, some prism poles are fixed. Some are adjustable. Most are adjustable because you run them up and down. Sometimes you need to see over a hill. Sometimes you need to get between branches on a tree. All sorts of reasons to run the pole up and down. Sometimes you want it run up because there's traffic going back and forth between you and the instrument, and you don't want that to be in the way. You want a clear line of sight. That notwithstanding, that distance there is called HR, height of rod. Okay? So, given this bit of information here, we need to find the elevation of this foresight point. Okay, we're going to call it the foresight point for the sake of this illustration. So the elevation of FS, that's the foresight point. That's whatever point you're shooting. Okay, you're pointing the instrument at that thing and you're making an observation. The elevation of the point you're going to have, or you're going to shoot, is simple. It's going to be the occupied point elevation, plus the HI. Go from here to here, right? Plus the vertical distance that we just calculated right here, minus the HR. That's the way you do it, and this is the concept. You start off on the ground. You measure up to get to the center line of this instrument. You then measure up, or in this example it's up. It could very well be down. It could very well be a negative number. You measure up to the level of the prism. Then you got to measure down the height of that prism pole to get the elevation of the point on the ground. We'll use this as an example. Let's just say, for the sake of this example, I'll make up some numbers. Let's say your HI equals 5.02 feet. And let's say your HR equals 4.96 feet. The pole I use at work all the time has a height of 4.96, so that's convenient. Well, give an example. if our occupied point has an elevation of 917, then the elevation of the Foresight Point of Foresight is going to equal 917 plus 502 plus 11.77 minus 4.96. You got no sine, cosine, or tangent and any of this stuff. This is just simply adding and subtracting. And we're going to try to do that here in our head. I don't know how successful we're going to be, but we're going to give it a try. 917 and 502 get you to 22.02. 22.02 plus 1177 gets you to 33.79. 33.79 minus 496. Well, 33.79 minus 5 gets you to 28.79. Add back 4 hundredths and you get 28.83 if I did the math correctly. So our elevation of Foresight equals 28.83 feet. Now, just out of lack of confidence in myself, we're going to get out the old HP 48 calculator. We're going to start off with an elevation of 917. Add to that our height of instrument. That gets you to 922.02. Add to that 11.77. Gets you to 933.79. Sounds familiar. Subtract 4.96 from it. You get 928.83. Well, I said 928.83. I forgot to write the 9 up there. Mental math shorthand. Mental math shorthand. If I know that everything I'm going to do is between 900 and 1,000, I can ignore the 9 completely. And I did. I ignored the 9 completely. I just forgot to add it in at the very end. But there you go. That is the elevation of that point. And that's the way we do it. If you have any challenge with that, just watch it over again. Maybe I'll do another illustration. But if you watch these videos going forward, we're going to use this exact same process, only it's going to be applied over and over again. So you'll get plenty of practice. Anyway, there we have it. An application of the reduction of slope distance and zenith angle to a horizontal and vertical component in a real world example. Thank you for your time. Look forward to the next one. Have a good day.